All right, where are we? Oh yeah, Lab 4 Part C. Hopefully you saved Lab 4 Part B script so you can go back over it as you see fit. Lab 4C is all about the geometric distribution. Lab 4 is about discrete random variables. There's a gazillion of them out there. We're only going to cover the generic one, which we covered in A, the Bernoullian binomial, which we covered in B, and the geometric, which we're covering in this section. It's a small part of this lab. This entire lab activity was about those discrete random variables. So by the end of this part of the lab activity, you're going to be able to plot a geometric probability function, both the probability mass function and the cumulative distribution function. You're going to be able to draw a random sample from this distribution and be able to determine likeliness of certain claimed outcomes, estimate the means, the standard deviations, the variances, etc. Same thing we did for part B, but here we're doing it for the geometric distribution. Again, if you haven't gone over the handout, which you need to download from D2L, about the 5 requirements of the binomial distribution, hit the pause button, read over that closely, and think about it. Because the geometric random variable violates at least one of those assumptions. Make sure you know which one. So let's start R as usual. Set the working directory. Double check that we're in the right place. Yep, again, notice lab4b.r. Start a new script. We'll go ahead and tile these vertically. Let's see where we are. Okay, so a related distribution to the binomial is the geometric, whereas the random variable in a binomial is the number of successes in n trials. That is, you know n for a binomial, you want to know the number of successes in those trials. In a geometric, you don't know n. What you do know is that you have one success, and the random variable is the number of failures before that first success. In R, the root for a geometric distribution is GEOM, which means, combining the prefixes, D GEOM gives us point probabilities, P GEOM gives us cumulative probabilities, Q GEOM gives us the quantiles, and R GEOM allows us random numbers from the geometric distribution. So here's an extremely interesting game. It's one that I came up with, and I'm going to patent and make $1 billion. I'm going to roll a single die, a fair die, a 6-sided die, until a 1 comes up. When the 1 comes up, the game ends. So what's the probability that the game ends on the first roll? Notice the question is not how many times does a 1 come up in 6 rolls, it's how many failures until I get my first 1. In the first, it would have been a binomial. Here, it's a geometric. So what's the probability the game ends on the first roll means that there were no failures. I got a success right off the bat. What's the probability the game ends on the 10th roll means I had 9 failures before I got my success of a 1. What's the expected number of rolls until the game ends? What's the standard deviation? If it takes 10 rolls to end the game, is it sufficient evidence the die is not fair? All of those questions we can answer based simply on what we did back in Part B with this new distribution. So, probability that the game ends on the first roll means that there's 0 failures. I want to calculate the probability that the random variable y is equal to 0. Since it's directly equal to, it's a d. Y has a geometric distribution. I want to know the probability that y is equal to 0. And the only parameter that geometric distribution needs is the success probability. And in this case, success probability is 1/6 because it's a fair six-sided die. So the probability that the game ends on that first roll is 1 in 6. If that surprises you, hit the pause button and think about it for a little bit. Go back over it a few times. Think, pause, rewind, pause, rewind. Think about it. What's the probability that the game ends on the 10th roll? If it ends on the 10th roll, that means that there was exactly 9 failures. D for exactly. 9 failures. 3% chance. If it ends on the 10th roll, there was a 3% chance of that happening, assuming the die was fair. Now, what's the probability that the game ends by the 10th roll? That means it could have ended on the first roll, the second roll, the third roll, the fourth roll, the fifth roll, all the way up to the 10th roll, which meant we could have had, as in the number of failures, anywhere between 0 and 9. So the probability the game ends by the 10th roll is actually asking us what's the probability that the random variable y is less than or equal to 9. And since it's a less than or equal to, the prefix is going to be a p, a cumulative probability. So the probability the game ends by the 10th roll is p, because it's less than or equal to geom 9, prob equals 1 over 6th. So that 83% chance. The outcome of 1,000 of these games, of these exciting games that for every one you play you have to pay me a penny for royalties, it's just going to be R, because you're looking at the outcome of 1,000 games. Geom of 1,000 games. And again, it's a fair six-sided coin. So there's the outcome of 1,000 games. And if you want to agree with me in terms of what I show up, let's go ahead and set the seed of 783. Run those two lines, and then we're going to agree on all of those outcomes. So for the first game, I had 0 failures before my first one. For the second game, I had 5 failures before my first one, which means my first one came on the 6th roll. For the 981st game, my first one came on the 4th roll. If you glance through here, you'll see some 22s, there's a 25 and a 24, there's a 29, so it can get up pretty high. In fact, there is no upper bound for a geometric distribution. If I want to, I could calculate or estimate the expected number of rolls to my first one. I'm going to recopy that, save this as a variable. I'm not just going to do it 1,000 times, I'm going to do it 1,000,000 times, or 1 times 10 to the power of 6, and then calculate the mean of OBS. Run those 3 lines, I get 4.996509. Now the actual expected value, which you should by now be able to calculate, is 5. Notice how close we came. And now if you think about it also, expected number of failures until my first success is 5. Expected number of failures until my first success at rolling a fair die, fair six-sided die, is 5. It's kind of interesting. And I can also get quantiles for that. These are the estimated quantiles. So I'm estimating that I have a 95% probability of having anywhere between 0 and 20 rolls before I get my first head, before I get my first one. So if I roll the die 30 times and don't get a 1, I have sufficient evidence to conclude that the die is not fair. Now, using the quantile function estimates the endpoints. Using the q prefix gives it to us exactly. So it's going to be q geom, and then we got to give it its quantiles. And then define the parameters of the distribution, the geometric distribution. And we get 0 and 20. Not too surprising. When you're dealing with discrete random variables, the estimates that you get when you do it a million times are most likely going to be pretty close, if not exactly the same as what you would get if you do it exactly. The same will not be true for continuous distributions. But for discrete distributions, this could be a really good estimate. Now the thing is, I have to ask this question: why would you ever want to estimate it using the quantile function when you can do it exactly using the q prefix? And the answer is, I don't know. And so here's the conclusion. By this point, the pattern should be very obvious. If not, you get to go over lab 4A, 4B, and 4C again until you actually see how obvious it is. Find the distribution. Usually you know the distribution based on how the randomness is defined. You're rolling a die, and you know how many times you're rolling it. It's going to be binomial. If you want to find out how many times you're rolling it, it's geometric. You find the stem for that distribution in R. For the binomial, it's binom. For the geometric, it's geom. For the hypergeometric, it's hyper. For the negative binomial, it's nbinom. For the Poisson, it's pois, etc. Determine what you want to calculate about the distribution and its associated prefix. If you want to calculate an exact probability for a single outcome, use the prefix d, as in d. If you want to calculate a cumulative probability, use the prefix p, as in p. If you want to draw a random sample, use the prefix r. If you want to find the quantiles, use the prefix q. The important part is figuring out what you want and interpreting what you got. Let the computer do the mindless calculations. You need to do the mindful stuff. I hope this was helpful. Good luck on the assignment. Take care. Bye.